Hey everyone, welcome to another episode. Today I'm going to be talking about some physics, and more specifically, this is going to be an introduction to the electrostatic force. Let's get started. So we might not think of everyday objects like this rock to have any electrical properties. However, when we zoom in on the molecular level, on the molecular scale, we can tell that this rock probably has something like 10 to the 20 or 10 to the 30 electrons, which are known as negatively charged particles. They also have an equal number of positive particles called protons, and that leaves this with a net charge of 0. So even though it seems as if this rock has no electrical properties, it in fact does when we zoom in and look at the molecular scale. So water is one such object. The water molecule is made up of 2 hydrogen atoms and 1 oxygen atom. And on the bottom end of this molecule, we have a net positive charge just on the bottom end. But then on the top, the oxygen contributes a negative charge. And so together, the water molecule is electrically neutral. But if you look at one side versus the other, you can tell that there's a dipole situation here. That means that there's one end with a net positive charge, this bottom end, and then the top end where the oxygen is has a net negative charge. Here we're going to observe a water molecule in the presence of a negative charge. And I'm going to simplify the water molecule. I'm just going to make it be an oval. Okay, and we're going to have a positive on top and a negative on bottom. That's just how it's going to be oriented for this problem. Now, if I bring in a charged object, a particle that is not neutral, such as an electron or a proton or any other positive or negative charged object, let's say that we bring in a negative charge here. What this is going to do, since opposite charges attract and like charges repel each other, is it's going to exert a torque on this water molecule, causing it to rotate clockwise. So the positive end of the water molecule is attracted to the negative particle that is influencing it to rotate. And so after some time, we will end up with this situation, where we still have the negative particle here, but the water molecule has rotated. And the only reason the water molecule rotates is because it's under the influence of this negative charge. Okay, so here I have an ordinary pen case. I just took out everything on the inside, and I have a bunch of cut up sheets of paper. This is my old physics homework, ironically, but don't worry, I didn't cut it up out of spite. So we see when I introduce this pen over the piece of paper, nothing happens. However, by rubbing the plastic pen piece, what I'm doing here is I'm breaking off tiny molecules on the surface and leaving a net charge on the surface of the pen. And this is a way that we know that wood, like water, is also a polar molecule. And so when I'm done rubbing this, I should be able to observe a charge happening. Maybe if I spread these out a little more, see a little movement. So basically what's happening here is the electrostatic force is overcoming the force of gravity on these pieces of paper. And if you think about it, I was talking about the rotation of molecules, and it turns out that the electrostatic force is dependent on 1 over the square of the distance between 2 objects. And so we'll see why that matters in a second. So I'll just draw a diagram real quick regarding what we just saw. So I had the pen case, and it was negatively charged after I had broken off some of the molecules on the surface, leaving them ionized, essentially. And then we had paper molecules introduced to the introduced into the influence. And so I'm going to draw two paper molecules, even though we had much more than that. And we can predict how they're going to rotate based on the charges on the dipole and the direction from which these water molecules is the plastic. So this is going to rotate clockwise, just like we talked about before, and same with this one. And so you'll end up with, after some time, the paper molecule is going to be rotated clockwise because of its influence by the negative charge. It's being influenced by the negative charge. But then something even cooler happens. Since the electrostatic force on any two charged objects is this formula right here. And that is, K is a constant, defined as 9 times 10 to the 9th power. And then the two charges are obviously just the two charges in question. We haven't given them values yet, but that will usually be given, or you find it somehow through algebra. And then R is the distance. And so we know that from this equation that the force, as the distance between these two charges increases, the force gets less by the square of this number. So if we are 2 times farther away, then the force is going to be 4 times less. If we are 3 times farther away, the force is going to be 9 times less. And the pattern continues ad infinitum. And so since we have this distance dependency, the force is dependent on the distance, we can tell right here that the distance from the negative charge and this positive charge is less than that of from the negative charge to the negative pipe. And because the positive charge is closer, it's going to have a stronger pull. It's going to pull this molecule. It's actually going to move it. It's going to move it this way. And so same with this one. Same thing happens. They're the same situation here. And so that molecule is actually going to experience an acceleration towards this negatively charged plastic pen casing. So now we're going to talk about metal. And this is going to be our piece of aluminum, and this is going to be our negatively charged piece of plastic. And when brought into the influence of this negatively charged piece of plastic, this aluminum has positive nuclei, in other words, protons that are structured in a lattice arrangement. But those positively charged nuclei also have electrons in their outer orbitals that are weakly held and are free to move around. These electrons are also known as conduction electrons. It's important to note that the net charge on this piece of aluminum was 0 before we brought it under the influence. And it is actually still 0 now, even though it looks like it has some charge because all the negatives are on one side and all the positives are on the other. But the piece as a whole is still electrically neutral. It still has the same number of electrons and protons, and they cancel each other out to therefore compose an electrically neutral object. And also the force on this block of aluminum will be attracted to this negatively charged plastic because the positive charges are now closer to this charged piece of plastic than are the negative charges. The negative charges would make it repel, but since they're not closer than the positive side, that means that these objects will attract. And so now we're going to talk a little bit more about Coulombs Law, which is this definition of the electric force that I gave earlier. And you'll notice that this thing looks a lot like another formula that you should have learned in Physics 1, and that would be the formula for the force of gravity. And that was big G m1 m2 over the distance squared. They're almost the same thing. The only difference is these absolute value signs. Since we know that the force of gravity is always attractive, we don't have to worry about that. But since there's positive and negative charges that we're dealing with here, that's important to put these absolute value signs, because this electrostatic force says nothing about the direction. You have to figure that out in other ways, and we'll jump into that. So in a lightning storm, electrons are allowed to transfer from a cloud through a person and into the ground. So let's say we have this negatively charged cloud up here. And then we have this person down here. You know, it looks like he's dancing or something. And we want to know, well, what's the net charge on this person? What sign of the charge first does he have? So he's standing on the ground, and because this has, it's mostly made of negative charges, what we can do is it's going to repel all the negative charges into the ground, and it's going to leave the person with a net positive charge. Now this is bad news for the person, as you can see why. The electrons from the cloud traveling down and being attracted to these positive charges and then taking the path of least resistance to the Earth, that is bad because that transfer of electrons is what we know as lightning. And so we're now going to put some numbers on this, and we're going to figure out the charge on the person and the direction the force, the electrostatic force, exerts on the person as a result of unfortunately being struck by this lightning above. So we're going to say that the cloud has a net charge of negative 15 coulombs. We'll say that the distance between the person and the cloud is going to be 500 meters. And we'll say that we are doing this calculation afterwards. We'll say that a force of 800 newtons is going to be working on this person. And so what we can do is apply Coulombs Law here. And this is easy enough. We just kind of plug it into the formula. So FES is going to equal K Q1 Q2 over R squared. Now remember, it's asking, we got to find out what the net charge is on the person. So we'll call his charge Q1 and this Q2. So I'm just going to flip this around for Q1 here, and we end up getting this thing. So that's just algebra. But we have all the values that we need now to solve for Q1. And so the charge on the person is going to be 800 newtons times 500 meters. Don't forget to square that quantity. And then this is going to be 9E9 times charge 2. We have it's negative 15 coulombs. So once we do that, and we punch this into our calculator, let's see what we get here. I'm just going to punch it in real quick. So the charge on the person, it looks to be 1.48 times 10 to the negative 3 coulombs. So that's good that we have that. And the force actually, the direction of the force we can get just by seeing that the person is positively charged to this and this is a negatively charged cloud. Well, opposites attract, so the force on the person is going to be upward. So I guess there are some instances where people have been struck by lightning and they end up flying up off the ground, meaning that essentially the electrostatic force that was acting on them, the interaction between the two, was greater than that of the force of gravity. So I think real quick I should just explain the whole factoring K thing out, and I'll just write kind of a general statement here. So if we have particles 1, 2, and 3, and we want to find the force on 2, let's say, we'll say that the net force on 2 is going to be equal to the force of 1 on 2 plus the force of 3 on 2. And so if we apply Coulombs Law here, we end up getting this. So Q1, Q2, because 1 and 2, that's the charges we're referencing for this first term, over R squared. And then we add Coulombs Law again, but now instead of using 1 on 2, we're going to do 3 on 2. So Q1, Q3 and then there's going to be a different distance, so I'll use capital R to denote that. And since they're all in a straight line, I can just say that this is going to be in the I direction. So if I just further simplify this even more, this is the whole factoring out K thing right here. We just pull these K's out, and I feel like that just makes it faster to type it into the calculator, and then we'll just keep everything else the same. And you don't have to do it this way, you can do it this way, but like I said, it's just more time consuming when you're typing all of these numbers into the calculator. And I know us engineering and science students, we like to manage our time, so that's kind of a general statement if you have charges 1, 2, and 3. So this brings us to the final problem in this video, and now we're just going to basically do 3 charges, but they're not going to be in a straight line. And so we're going to have charges A, B, and C. And what we have to do here is we have to know their locations. So we're going to put A having 10 microcoulombs at the origin of a graph. So this is going to be at 0, 0, and then B and C are going to be located at 40, 30, and so B is at 40 centimeters, comma 30 centimeters, and then C is just going to be at 40 centimeters, negative 30 centimeters. So those are the coordinates on the plane if A is at the origin. And we've already named all the charges. One thing that we have to get first when we're dealing with angles, so if we want to find the net force on A due to B and C, then we're going to need an angle. And by the way, B and C are going to be 25 microcoulombs each. So now we have all the information that we need. So we're saying that this is at the coordinate 4, negative 3, and this is at the, 4, positive 3, and this is 4, negative 3. And so now that we have that information, we can find the angle by taking the inverse tangent of y over x. So that is going to be, looks like 3 over 4. And that angle we get is 36.9 degrees. So that is the angle. So if we draw this out here, that is this angle here. And now to find the force on A. So we can denote this by, like we did last time, just net force on A is going to be equal to the force of B on A in the x direction. So we're going to have to figure out both the x and the y directions because there's x and y components, or in other words, horizontal and vertical components. And then so that's going to be the force of C due to C on A in the x direction. And that turns out to be, so it looks like what we have here is positive charges. We have 2 contributions in the x direction. These charges are going to push on A in the negative x direction. And so we can start out by writing our negative sign. And since the contribution, both of these are the same charge, so the contribution is just going to be 2 times what one of them would be. We then put our constant in there, and since we have an angle and we're dealing with the x direction, we put cosine theta. And then it looks like what we're going to do next is put our charges and our radius. According to Coulombs Law, this is just going to be, well, let's just put Q of, so the force on A due to B is the same as the force due to C on A. And that means that we can just use either one of these. Since I've already accounted for both of them by putting this 2 scalar here. And what that does is basically allows us to just use one of these charges and the charge on A. So 25 microcoulombs and 10 microcoulombs. So that's going to be QB times QA, which is the same thing as QC times QA. So I can just write one of them again because I just put the scalar constant 2 there. And then the distance between them, okay? We can use the Pythagorean theorem to find the distance of this between the 2 charges, B and A or C and A. It's going to be the same distance, either one we use. And how we do that is basically that's just going to be the square root of x squared plus y squared, and then remember that's the radius, but then we have to square it. So that's like our general formula to get the force in the x direction. And I guess when we plug the values in, we'll get -2 times 9e9 times the cosine of our angle, which is 36.9 degrees. And then we'll just plug our charges in, so that's 25 micros and 10 micros. And divided by the radius squared, so it looks like, let's see, what would that be here? So x is going to be 40 centimeters, so we can do square root of 0.4 meters plus, and then the y, which is 30 centimeters, or 0.3 meters. And then we square them. And so the forces in the x direction are going to be whatever that is when I punch it into the calculator. And so let me just see here. So -2 times 9e9 times cosine of 36.9 degrees. And then times this fraction, which is going to be 25e-6 times 10e-6 divided by the square root of 0.4 squared plus 0.3 squared. And then we're going to square that. And this should give us the force in the it's going to give us the force on A in the x direction, denoted by these subscripts here, which happens to be -14.4 newtons in the negative x direction. And that's basically all there is to it for the x. Now, for the y, this is actually pretty easy. So now we're going to look at how B affects A in the vertical direction. So they're both positive charges. So that means that B is going to push A down. But if we look at C, it's also a positive charge, and it's going to push A up. So by looking at the diagram, we can just tell that the forces in the x direction, or sorry, the forces in the y direction are going to equal 0. And therefore, that just leaves us with the force in the x direction. So the net force due to A, the net force on A is going to equal this -14.4 newtons in the x direction. And so that's a common classic problem in physics 2. Basically, we got the angle, we got the distance that this line is right here, this hypotenuse, and we doubled this value because these two charges are the same. They're making equal contributions, but there's 2 of them. So we can write one expression and then just double it. And then we knew that it was in the negative direction only because this charge is positive and this charge is positive, and so they're both going to be pushing on this positive charge in the negative X direction. So I hope you guys find that helpful. So thank you for watching another episode of Aerospace Engineering with Brian McNulty. Today it's been a lesson on the electrostatic force and how it kind of can be found by knowing the charge and the distance between two charged particles in the universe. Please like and subscribe to the video, and if you have any questions, just leave them in the comments below. I'll see you on the next episode.